Welcome to the fifth class on series. So today we will talk about integral test and some of the examples. The ultimate goal of this video is to prove the P series test. I will come to P series test, but before that let me tell you what do you mean by an integral test. So what is an integral test or the integral theorem? It says that suppose if you have a series summation an, this is my series where an's are real numbers. Suppose if you are able to define a function f which is continuous, positive and decreasing. If your function is satisfying these three conditions, and when you replace your x by n, you are getting nothing but the terms of the series. So after some stage, so n is the state, so suppose n is equal to 100. So from 100 onwards, whenever you replace your x by n, what you are getting but nothing but the terms of the series. So if you have such a nice function, then what does the integral test says? That integral n to infinity f of x dx and summation n from n to infinity an both converges or both diverges. Means your integral and series both behave in the same way. So whenever a series is given to you, we try to define a function satisfying this 3 and this 4th condition, and then you try to evaluate this integral. And once we know this integral, once we know the behavior of this integral, your series will also behave in the same way. So if the integral is convergent, your series will also converge. If the integral is divergent, your series will also diverge. So that's what the integral test is. One more point to take care of is, if this integral is convergent, by this test series also is convergent, but it does not say that they both converge to the same number. Like if suppose if this integral is converging to a number L, so I know that this is also convergent series, but then there is no guarantee that this will also converge to the same number. So it only tells us about the nature of the series, it doesn't tell at which number it converges. So that's one point to take care of. So this is integral test. Now let's take some examples. So if I take suppose summation 1 upon n plus 4, n is running from 1 to infinity. I want to see whether this is a convergent or a divergent series. So what you do is, you try to define a function. Usually what to do is, we replace our n by x, and whatever we get, we call it that as a function. So you take f of x to be this. Now for all x greater equal 1, one can see that your f of n is nothing but your an, because when I replace x by n, I am getting nothing but the terms of the series. What is an? This is my summation an. What is an? 1 upon n plus 4. So my function is satisfying this condition that I am replacing x by n, I am getting the terms of the series. Now is my function continuous? Yes, because this is not defined at -4, but I am talking about greater than 1. So this is continuous, this is continuous, ratio of two continuous function is continuous, that is one point. Is this a positive function? Yes, because my x is greater or equal 1. So this is positive, so ratio is positive. Is this a decreasing function? Yes, because if you take the derivative of this, what is the derivative? -1 upon this whole square. So derivative is negative, therefore function is a decreasing function. So all the conditions are satisfied. Now only need to check is whether this integral converges or not. So integral 1 to infinity f of x dx. What is this? This is 1 to infinity 1 upon x plus 4 dx. Now this is improper integral. So how do you solve? Limit integral 1 to a 1 upon x plus 4 dx. A goes to infinity. This is limit a going to infinity. What is this? Log of x plus 4 1 to a. And when I put this over here, limit a going to infinity, log of a plus 4 minus log 5. And as a goes to infinity, log is an increasing function, so this goes to infinity. So therefore your integral diverges, and since this integral is diverging, therefore by integral test our series also diverges. So this is how one can solve the problem using integral test. Let's modify this. Suppose if I take 1 upon n square plus 4. If I take 1 upon n square plus 4, then what will my f of x? We will take f of x as 1 upon x square plus 4 for all is greater or equal to 1. This is true. Now 1 upon x square plus 4. 1 upon x square plus 4. What is integration of 1 upon x square plus a square? It is 1 upon a tan inverse of x by a. And you solve this. When you solve this, what you'll get? You'll get something to be a finite number. You will get something to be a finite number. And therefore, since this integral is convergent, therefore the series converges. You need to check that your function is satisfying all the conditions, right? This is fine. When I replace x by n, I am getting the terms of the series. Is your function positive? Yes. Ratio of 2 positive is positive. Is your function continuous? Yes. 1 is continuous. X square plus 4 is continuous. So ratio of continuous function is continuous. Is it decreasing? Yes. You take the derivative. Derivative will come out to be negative, and therefore the function is decreasing. So all the conditions are satisfied. Therefore, summation 1 upon n square plus 4 is a convergent series. I don't know where it will converge, but I definitely know that this is a convergent series. So there's the second example on integral test. Now let me take the last part of this section, which is one of the very important theorem and which we'll be using very widely in the coming lectures, which is nothing but a P series test. What does the P series test says? It says that summation 1 upon n raised to p, where n is running from 1 to infinity, this converges for p greater than 1, diverges for p less equal 1. So this is what we want to prove. So this is the main goal of this test, to prove the P series test. So let's do this question by taking some cases. So let's take the simplest case, case 1, when my p is 0. When my p is 0, what do I have? Summation 1 upon n raised to 0 is 1. So nothing but 1 plus 1 plus 1 plus, adding 1 infinity times, what I get? I get infinite. So therefore this is a divergent series. One can directly write this as infinite, or another way is, this is what? This is a1 plus a2 plus a3. And what is limit of an? Means when you look this an as a sequence, means a1 comma a2 comma a3, but all the terms are 1 1 1 1 1. So what is 1 comma 1 comma 1 comma 1? This is a constant sequence, so it converges to 1, which is not equal to 0. Therefore by nth term test, your series diverges. So therefore when your p is 0, the series is a divergent series. It diverges. Case 2. Suppose your p is negative, p is less than 0. That means what? Your p is equal to minus k, where k is positive, because any negative number is what? Minus of a positive number. So suppose your p is negative, that means your p is minus k. So how the series will behave? In that case, the term which were in the denominator will come in the numerator. So summation 1 upon n raised to minus k, n running from 1 to infinity. This is summation n running from 1 to infinity, n raised to k. And this diverges. Why so? Because what is this? This is 1 comma 2 raised to k comma 3 raised to k comma 4 raised to k comma n raised to k, where k is positive, where k is positive. So I'm taking the powers of a positive number. And so therefore this as a sequence diverges, and therefore by nth term test, summation 1 upon n raised to p diverges. So we are done with the case of p less equal 0. Now only case left is p greater than 0. So now let's take that case. So only case left is case 3, p greater than 0. Now I will take the help of the integral test. So define the function as f of x as 1 upon x raised to p. One can see that the function is p is greater than 0, okay, and my x is also greater equal 1, because my series starts from n equal to 1. So my f of n is nothing but an. My function is a continuous function because 1 is continuous, x raised to p is continuous. It's a decreasing function because the derivative is negative. What is the derivative of this function? F dash of x is nothing but minus p upon x raised to p plus 1. Since p is positive, x is positive, so therefore the derivative is negative. Therefore my function is a decreasing function, and it's a positive function because ratio of two positive numbers is positive. So therefore it's a positive function. So now all the conditions of integral test are satisfied. So therefore now let's solve this integral. Integral 1 to infinity 1 upon x raised to p dx. If you try to solve this, it is nothing but limit a going to infinity, integral 1 to a x raised to minus p dx, limit a going to infinity, x raised to minus p plus 1 upon minus p plus 1, 1 to a. This is limit a going to infinity, a raised to minus p plus 1 upon minus p plus 1 minus 1 upon minus p plus 1. So this is what I have after solving this integral. And now one can see that now p is greater than 0, right? Now here also we further make some cases. If my p is, I know it is greater than 0, if my p is less than 1, if p is less than 1, this term will remain in the numerator, means your a will remain in the numerator because the power is positive. And as a goes to infinity, your integral 1 upon x raised to p dx is what? Infinite. And if your p is greater than 1, if p is greater than 1, then this power is negative, therefore a will come in the denominator, and therefore as a goes to infinity, I have 1 upon infinity, which is nothing but 0, and what I get is this term becomes 0, I get 1 upon just minus 1 upon 1 minus p. This is what I get, and that's what the proof is. So for p less than equal to 0, we show its divergent. For greater than 0, we are taking this as a function and we are solving the integral. Here also two cases, if p is less than 1 and if p is greater than 1. If p is less than 1, then it diverges. Therefore by integral test, your series also diverges. For p greater than 1, integral converges, and therefore by integral test, for p greater than 1, this integral converges, and therefore by integral test, your series also converges. So therefore, by integral test, summation 1 upon n raised to p diverges for p less than 1, converges for p greater than 1. And when your p is equal to 1, I need to solve that case separately. So now only case left is p equal to 1. So when p is equal to 1, what is this integral? Integral 1 to infinity 1 upon x raised to p is 1. This you try to solve. 1 upon x integration is log x. It will come out to be infinite, and therefore for p equal to 1 also this diverges. So therefore the integral diverges for p less equal 1. So that's how you prove the p series test. So this is the p series test which we are going to use very frequently. So I hope the proof is clear. All the cases are clear. If you have any doubt, you can ask me in the comment section. Thank you.